of this book, by the way, you can find this book in our library. In our library, you can find this book. So you can also find this book in the internet on our site of our chair of our Department for Theoretical Physics. First lecture today, first paragraph of our lecture is two-state quantum system. Двостанові квантові системи, two-state quantum system. Quantum system. It's first paragraph. One of the simplest quantum system, it is just two-state quantum system. What it means? It means that quantum space is two-dimensional. Two-dimensional quantum state. It means that we have two basis vectors, and we can notate these vectors as 0 and 1. For instance, it can be spin system, spin 1/2. As example of two-state quantum system is two-dimensional quantum system. It is spin 1/2, and state 0 can be associated with arrow up, and state 1 is associated with arrow down. So it is one of the simplest quantum system, two-dimensional quantum system. It is spin 1/2. So arbitrary is an arbitrary state. In this case, can be written as linear superposition of these two basis vectors. So arbitrary quantum state, it is linear combination. Let's write here C0, 0 plus C1, 1. Or in spin notation, it is C0 arrow up plus C1 arrow down. It's absolutely the same. So we have such notation. 0 is related with state of spin, which is directed along z-axis in positive direction, and 1 is related with direction of spin in opposite direction. Let me recall you that when we have three-dimensional space, so it is such orientation of spin, it is arrow up, and opposite direction of spin, it is just arrow down. We considered some exercises on this problem, so you remember this. Arbitrary, I would like to say once more, so arbitrary quantum state of two-dimensional system can be written in such a way, and such quantum system presents quantum bit. So two-dimensional quantum system is associated with quantum bits, which is called qubits or quantum bits. So such quantum state of two-dimensional quantum system represent quantum bits. So here we have some new notion which is used in quantum information theory. It is quantum bit. And here is a very interesting relation between quantum bit and classical bit. And before considering some mathematical properties of two-dimensional quantum state, let me show some relation between classical bit and quantum bit. So therefore, here I would like to show you just this relation. And let us start from classical bit. What means classical bit? But before considering the relation between classical bit and quantum bit, maybe you have some question to this introduction, to this subject, two-state quantum system. Чи маєте якісь запитання до ось цього? Ну і щось скажіть, щоб я почув, що ви мене чуєте. Добре, я хотів ще вас попросити, якщо до нас зайде начальство, яке нас перевіряє, то ви мені дайте знати. Я маю до них, якщо ви побачите, бо я не дуже слідкую за екраном, а пишу, тому не бачу, хто там заходить. So, what means classical bit? Classical bit, it is some classical system which has two stable position. For instance, we can consider two boxes. And when particle is in the first boxes, it is associated with 0, for instance, and it is some another situation when particle is in the second box. So this position of particle can be associated with 1. So we have two possible classical positions. When some particle is here, then it is such situation is associated with state 0, and here we have another situation that when particle is in second box, and this situation is related with state 1. So it is a simple presentation of classical bit. When particle is in one box, we have 0 state 0, and when particle is in the second box, we have state 1. It is classical status. We can only have such situation or such. We cannot have particle in one and in second box at the same time. So it is very difference between a quantum case. And let us write this situation, classical situation, in very similar way as in quantum case. So when particle is here, I here write 1, and here is absent particle is absent, so I write 0. And this, we have the following situation. Here it is 0, particle is absent here in the first box, but here we have 1. So such presentation of a classical bit is very similar to quantum case. Maybe you remember that this state in matrix representation has the following way, representation, and here we have 0, 1. So it is very similar to the case of classical case. But what is difference between classical case and quantum case? In classical case, we cannot have superposition of these two states. We have only 0 or we have only 1. Only 0, only 1. But in quantum case, it is classical case. But in quantum case, when let us consider a superposition principle, when quantum system can be in state 0 and can be in state 1, then quantum system can be also in state which is superposition of these two states. And this superposition is written just, let me write here once more, this superposition psi, which is superposition of these two states. We just represent quantum bit. So instead of classical bit, where a classical system can be in state 0 or in state 1, in quantum case, a quantum system can be in state at the same time in state 0 and in state 1. It is superposition of these two possible states, 0 and 1. So we have very difference between classical and quantum case. So, and it is very important that such situation is really realized in the nature. It is, for instance, spin 1/2. So quantum system live in such a way that superposition principle give the possibility to have such a state where we have a linear combination of these two states, 0 and 1, instead of classical case. It's very, very different between quantum and classical case. So here we considered classical bit and quantum bit. I think that I explain difference between classical bit and quantum bit. So quantum bit is called qubit or quantum bit. So, and I would like to ask you here, maybe you have a question to consider about classical and quantum bit. Do you have some question? So I would like to hear you about question concerning classical and quantum bit. Чи маєте якісь запитання стосовно класичного і квантового біта?
Та ні.
Нема, добре. Ну, то ще раз вже тепер скажу по-українськи. Значить, головна різниця. Класичний біт може бути в стані 0 або в стані 1. Не може бути в стані, який є одночасно і 0,1. Або тут, або тут. В квантовому випадку він може бути квантовий біт. Він може бути одночасно і в стані 0, і в стані 1. Це є суперпозиція. So, and now I would like to mention about spin operators. You remember these operators. It is related with Pauli matrices, but it is very important. So let me recall this subject once more. We considered some exercises on this subject, but nevertheless. So it will be fast. And now let us consider next problem of our lecture. So spin operators. Spin operators. So spin operators, as it is Planck constant divided by 2. And here we have Pauli matrices. Pauli matrices have 3 components, sigma x, 0, 1, 1, 0. Y, it is 0, minus 0. Z component, 1, 0, 0, minus 1. So because we have two-dimensional space in matrix representation, matrices is 2 by 2. So all operators in two-dimensional quantum space can be represented as matrices 2 by 2. So we have matrices 2 by 2. It is operators in quantum in spin space. And one of the important operators in this case, it is just spin operators, which is related with sigma matrices or Pauli matrices. So some properties of Pauli matrices. You remember the following properties. Anticommutator of these two matrices, sigma alpha, sigma beta, is 2 alpha beta. It is 2 multiplied by 1 when alpha equal to beta, and it is 0 when alpha is not equal to beta. Important from here, you can find that arbitrary sigma matrix squared, it is 1. You can verify these properties using this representation of Pauli matrix. It's very simple problem which you can prove without any problem, I think. So concerning the notation, okay, it is written here, but let me write here once more. So notation, sigma z, eigenstatus of sigma z is arrow up. It is with eigenvalue 1, and sigma z acting on arrow down. It is -1, arrow down. In matrix representation, these vectors is the following 1, 0, and arrow down, it is state 0, 1. So when we have arrow up, here we have 1, and here we have 0, arrow down, here we have 0, here we have 1. So what's the next important? Okay, the next very important is eigenvalue equation for the following operators. We considered this problem. It is eigenvalue problem for these operators, can be written in such a way. This operator it is projection of spin on direction A. So when we have some direction A, and we have some spin, so this operator represents the projection of spin on this direction, on direction A. So really, it is in fact, what means scalar product? Scalar product means the product of sum of all products of components, sigma x AX plus sigma y AY plus Z component. It is scalar product. So you can easily calculate this scalar product, substituting this representation for matrix. You can write these operators. It is a very simple problem. And as a result, we obtain the following. Let me write only this operator, and next I write only the result. We consider it as exercises, this problem. So I would like to omit details of calculation and write only the result. So this operator, this operator is denoted as A. So this operator will be the following. Sigma x, it is operator matrix representation 0, 0, 1, 1, and this vector, which is related with direction, can be written in polar coordinates and represented by two angles. So let me write here x, it is sine theta cosine phi, so substituting this result, we obtain that it will be, let me write here, the next component 0 minus I complex unit is that component, and that component 1, 0, 0 minus 1. So we can add these all matrices, and as a result we get the following representation for operator A. Cosine theta, cosine with minus. And here we have sinus theta, exponent here we use the Euler formula for this expression. You remember this formula? It is cosine phi minus I sinus phi. So operator which represents the projection of operator, spin operator on some direction, can be written in such a way. And you can, without a problem, to solve eigenvalue problem, and it is eigenvalue problem for matrix A. And from linear algebra, you know this problem, and you have many exercises on this problem. So here we have the following matrix equation, eigenvalue matrix equation. Here are some components. I write components I small a and b. It is component of wave vector, vector of in this space psi. It is psi, eigenvalue vector of this matrix. Then we have eigenvalue, and once more the same state a b. So it is eigenvector, and it is eigenvalue. It is eigenvalue. So you can solve this equation, and as a result you obtain an eigenvalue of this equation. You have two possible eigenvalues, lambda equal to 1 and lambda equal to -1. And here we have eigenstate, which corresponds to this eigenvalue, and eigenstate, which corresponds to this eigenvalue. Let me write it as psi plus. This plus corresponds to this +1. And after solution, you obtain the following result. Cosine theta, arrow up, plus sine theta, exponent, arrow down. And here you obtain psi minus, which is the following, which is very similar to this, only here we have minus sine, sorry, here theta divided by 2. I'm sorry for this mistake, divided by 2, arrow up, plus cosine theta over 2, exponent, arrow down. So we have two, but in these books I use some another notation. It is notated, this vector is notated in such a way. Let me write the notation as it is written in book. It is psi, psi. Here is written this vector, and here is plus. Here I use some additional notation which is related with this direction, I. So here is direction I, and here is just this plus. But here I use some simplified notation. I don't write here the direction of this vector I, but only write plus, which is related with this plus, and the minus, which is related with this minus. So we have two solutions of this eigenvalue equation, and two eigenvalue and corresponding eigenvectors. And in matrix representation, this eigenvectors is here. Here you have put matrix representation 0, 1, and here you can put 1, 0, 0, 1, and substituting you obtain matrix representation for this vector. Really, after this substitution, for instance, psi plus can be written in such a way. It will be cosine theta divided by 2. And here we have component sine theta by 2, exponent phi. So it is solution for solution of eigenvalue of equation for projection of operator on some direction I. So maybe you have here the question concerning this eigenvalue equation. I would like to say also, I forget to show you important fact. This important fact, when you look at this matrix which corresponds to this physical value, you can easily find that this matrix is a Hermitian matrix. So without any problem, you can show that this matrix is Hermitian matrix. And you remember from linear algebra that eigenvalues of Hermitian matrix is real, and eigen function or eigenvectors is orthogonal. So here you can find that eigenvalues is real, and it is related with the fact that matrix is Hermitian, and eigenfunction or eigenvectors which corresponds to these eigen values are orthogonal. So really, let me show that these matrices, these eigenvectors are really orthogonal. Let us consider scalar product psi plus, psi minus, and but before calculation, let's write this. Bra vector. Bra vector will be the following. Let us look here. It is ket vector, and now let us write bra vector. So as result for bra vector, we obtain cosine theta divided by 2. Bra vector arrow up plus sine. Here we have minus, and bra vector for arrow down. So then for scalar product, we obtain, let me write here once more this result. It is multiplied minus sine so we obtain. So arrow up, it will be a scalar product of these two vectors will be 1. So we obtain minus cosine theta and sine theta by 2 divided, okay? And then arrow up, sorry, I forget to write here arrow down. Arrow up, arrow down, it is 0. Then arrow down, arrow up, it's once more 0. And here we have non-zero result only here, production of arrow down and this arrow down. So we obtain plus sinus theta divided by 2, cosinus theta by 2, and here we have product of these two exponents, it is 1. So as a result, it is 0. So scalar product of these two vectors, which corresponds to different eigenvalues, is 0, as it must be. So when we have eigenvectors of Hermitian operators, which corresponds to different eigenvalues, so this scalar product will be 0, and we verified that it's really 0. Okay. So seems I write here important facts from spin operators as properties of eigenvalues and eigenfunction or eigenvectors of spin operators. So maybe you have some question or comments.
Ні, немає.
Okay, so next subject will be considered. We can okay. So what we consider next paragraph of this book. Хтось щось має якісь запитання? Okay, we consider the next paragraph, which is called spin density matrix. Spin density matrix. Next paragraph, spin density matrix. So we consider pure state, which is described by spin state psi, and this spin state let me write in the following way. It is C up arrow up plus C down arrow down. So I think that you understand this notation. So this coefficient C up related with this vector and C down related with this vector. So it is arbitrary state of spin 1/2. And when we have a pure state, so density matrix rho of pure state, you remember, it's such operator. It is density matrix of pure state. What means pure state? Pure state means that we have a set of quantum system, which is each system is in the same state. So it is just pure state. It means that we have one system in state psi, we have second system in the same state psi, and so on. Next system in state psi, and so on. It is pure state. Чистий стан. Pure state. And density matrix for this pure state can be written in such a way. And let us consider matrix representation for this pure state. In order to get matrix representation, we substitute this state here and here, bra vectors, and as a result, we get the following. So let me write here we have ket vector, sorry, C up, C down, multiplied by the following bra vector. C up, complex conjugation here we have. Plus C down. As a result, we obtain the following: C up, plus C up, C down. Sorry. Plus the next product, we have C down, C up, And finally, we have C down, and operator, sorry, bra vector, up, up. So this operator in explicit form can be written in such a way. We can write in matrix representation without any problem this result. So in matrix representation, we obtain the following. In matrix representation, first element will be this one, C up, C up. Here we have C up, C down. Here I have C down, C up, C down, C down. So density matrix for this pure state can be written in this way. And now we will write this matrix in some another way, use some properties of this matrix, which we can find now. First of all, I would like to say that this coefficient C up and C down is not independent. It is, this coefficient is related by normalization condition, C up squared plus C down squared, it is 1. It is normalization condition which follows from the following notation. Scalar product C by psi vector by the same psi vector, it is 1. From this follows this normalization condition for these coefficients. So this coefficient C up and C down, using this scalar product, which is must be equal to 1, we obtain this condition. So using this condition, now let us rewrite C matrix, density matrix rho. First of all, you can see that sum of these diagonal elements is equal to 1, because it is C up squared, it is C down squared, and this sum is equal to 1. So sum of these diagonal elements is 1. You remember the properties of density matrix, that sum of diagonal elements or trace density matrix is equal to 1. And here you find that it is really, we really have these properties. So in order to rewrite this density matrix, let us take into account the fact the sum of these elements, sum of these diagonal elements is equal to 1. So it means that we can write, let us write this C up squared, let us write as 1 plus some real values, let us write in such a form AZ. I don't know at the moment, we don't know what means this parameter, but we know that it is a real value, so we can write this real value as 1 plus something. And C down squared, we write as 1 minus a real value AZ. So then sum C up squared plus C down squared is 1. So we always can write these real values in such a way. It is first fact which we take into account. Okay, the next, what is next important fact? Let us look here. It is some complex number. And here we have also complex number, but this complex number is conjugated to this one, and opposite, we have that this complex number is conjugated to this one. So let us write this complex number, C up, C down, conjugated in such a form, some real value AX. Here it is convenient to write minus AY. Why I use just such notation, we will see in future. But now let us use just this notation which I write here. And then, okay, C down, C up conjugated, it will be AX plus AY. Really, this number is conjugated to this one. Therefore, here we have, instead of minus, here we have plus. So this complex number, which we have in this matrix, can be written using three parameters: AX, AY, and AZ. So then let us rewrite density metric in such a way. But sorry, I forget. You can find the mistake here, written here. Maybe you find the mistake. So I would like to ask you to find the mistake. Is this for? Yes, here we must write 1/2, and here 1/4, because some of this number must be 1. In order to have 1, here we must put multiplier 1/2. 1 divided by 2. So then similarly, it is convenient to write here also 1/2, because it is, in fact, it is arbitrary parameters A. So it is convenient to write here 1/2. Here we must write over 2, but here it is convenient to write 1/2, similar as is here. So then we obtain the following matrix: 1/2 I write here, and here we have matrix 1 plus diagonal element. The next will be 1 minus, and here we have x minus so we have such a matrix. But now let us write this matrix in the following way: 1/2, and let us combine this one and this one. It will be diagonal matrix. So let me write here such a bracket, and here we have matrix 1 0 0 1. It is just this matrix plus what we have. Now let us next matrix write multiplier AX, and here we have matrix. Here will be 0. Here we have 1 1 0 plus. So we consider a matrix related with this multiplier. Then next matrix Y. So this matrix. So we have 0 minus I 0, and finally we have matrix related with this parameter AZ. So here and here. So matrix will be 1 0 0. Here we have minus 1. So this matrix can be written as sum over these four matrices. It is diagonal matrix, unit matrix. So it will be. So we have the following result: diagonal matrix. Так, зачекайте хвильку. Я щось не знаю, де ключ. Я не знаю, може він не у вас. Окей, ніби я був там, але трошки не клав, може прийти. Окей, можемо продовжувати. So you can continue our lecture. Ви чуєте мене, так?
Так.
So it is unit matrix. I write here unit matrix plus this parameter AX. It is matrix, Pauli matrix. X component of Pauli matrix. Plus similar here. Sorry, A, then Pauli matrix, plus finally Z component of Pauli matrix. But here we have nothing more a scalar product of some vector A with sigma. So when we consider this component as some component of vector, so let's write here. Let me write here. Let us introduce vector I, which have component X, Y, Z. So then we can rewrite this density matrix. We can rewrite density matrix in this way. So density matrix row, it is the following way. It can be rewritten Y plus, here we have scalar product, this vector I multiplied by Pauli matrices. So density matrix of spin 1/2 pure density matrix of pure state can be written in this way. And this vector, length of this vector is equal to 1. Now let us really show that length of vector I is equal to 1. It can be easy showed. It is necessary to let me consider it the result right in here. So here let us consider product of these two formulas. So as a result, we obtain that C up squared multiplied C down squared, it will be 1/4, while 1 minus AZ squared. And here, when we multiplied these two formulas, left and right side of these formulas, you obtain once more that C multiplication of this complex number with this one gives the following: C up squared, C down squared. It will be 1/4 and then what we obtain, ax squared plus ay squared. So it means that it is the same. So this result is equal to this one. So we obtain that 1/4 can be cancelled. 1 minus az squared is equal to ax squared plus ay squared. So putting this value here, we obtain that ax squared plus ay squared plus az squared, it is 1. So length of this vector is equal to 1. So in fact, we have only two independent parameters in this density matrix. Only, sorry, just a moment. So in fact, we have only two independent parameters because the length of this vector is 1. We have only two parameters which is independent. It can be related with the angles of this vector. So when we consider this vector in some three-dimensional space, A, so this vector can be, direction of this vector can be represented by angle theta and phi. And density matrix of pure state of spin 1/2 is presented by two real parameters. And these two parameters can be considered as two angles, which we write here. So you remember that arbitrary quantum state of spin 1/2 has two real parameters, depend only on two real parameters. And absolutely the same result we must have for density matrix. And we can verify here that really density matrix of pure state has only two independent parameters, two independent real parameters. And these parameters can be associated with these angles. And the arbitrary quantum state of pure state of spin 1/2 is given by this vector. Changing this vector, we have some another quantum state. So with points which we obtain by these vectors, we obtain a different quantum state. But this vector with length 1 presents sphere of radius 1. And this sphere is called Bloch sphere, sfera Blocha. And we have a very interesting mapping. We have that all, or maybe arbitrary quantum state can be presented as a point on this sphere. So we have the following fact: space of spin 1/2, quantum space of spin 1/2, it is sphere, and each point on this sphere is related with some quantum state. So qubit, because you remember that spin is in fact spin 1/2 presents some qubits, quantum system which we call qubit. So qubit can be considered as a sphere of radius 1. Space of qubit, it is sphere of radius 1. All pure state is related with this Bloch sphere. So here maybe you have some question. Чи маєте якісь питання? Значить, ще раз, матриця Устини може бути представлена спіна одна друга, чистий стан, ось такий спосіб, де ось цей вектор А, це є одиничний вектор, одиничної довжини, length of this vector is equal to 1. І є таким чином, оскільки три параметри пов'язані цим співвідношенням, тільки два незалежні параметри. Це можуть бути, наприклад, кути в сферичній системі. І тоді кожна точка цього вектора відповідає певному квантовому стану. Так що всі квантові стани можуть бути асоційовані з точками на сфері. І є відображення, мепінг квантового стану на сферу. І ця сфера називається сферою Блоха. Ось така візуалізація цього квантового простору – це є сфера Блоха. Значить, space of quantum state of spin 1/2, it is sphere of radius 1. Okay. Do you have some question?
No.
Okay. Добре. Let us consider the next question. Let us consider eigenvalue of density matrix. So we consider this equation. What is eigenvalue of this matrix? Let us put here density matrix. It is 1 plus scalar product sigma to every matrix. And here eigenfunction or eigenvector, it is lambda. We can rewrite this equation in the following way. What we obtain 1 minus 1/2 So So you remember that eigenvalue of this operator, of this one, this operator is equal to what is eigenvalue of this operator? It is 1 and -1. So what we obtain? So in order to get here 1 or -1, what we obtain for lambda? So for lambda we must have, not correct. Eigenvalue of this operator, eigenvalue of this operator is 1 or -1. So when we put here, okay, all is okay. So because this one is constant, so okay. Let us consider in such a way, without rewriting in such a way, it's more simple. So eigenvalue of this operator, it is 1 or -1. So when we put here 1, you obtain that lambda will be 1 over 2, 1 plus 1, it will be 1. When we put here -1, once more, -1, so what we obtain, 1 minus 1, it will be 0, so then lambda, it will be 1 over 2, 1 minus 1, it will be 0. So you can easily verify that eigenvalue of this density matrix is 0 and 1. Because you remember that we solved eigenvalue equation for this scalar product, and this eigenvalue is 0 and 1. As a result, these eigenvalues will be, so this eigenvalue is 1 and -1. As a result, this eigenvalue, for this eigenvalue we have 1 and 0. So density matrix of pure state of spin 1/2 is 0 and 1. And you remember that for pure state, at the end of the previous lecture, we obtained the following results, that for pure state, for the eigenvalue of density matrix of pure state is 1, and next eigenvalue is 0. And here you can verify that similar properties we have for spin 1/2 as it must be for pure state. Okay, we can finish it, this subject, which we call this paragraph. It is spin 1/2 and density matrix of pure state spin 1/2. Next problem which we considered is density matrix of spin 1/2, mixed density matrix of mixed states of spin 1/2. So mixed state of spin 1/2. So now we consider mixed state of spin 1/2. Let me consider it the case when we have mixing of two pure states. Let us we have first pure state, which is described by density matrix rho 1, and next pure state describing by density matrix rho 2. So first density matrix is, let us write in such a way, 1 over 2 unit matrix, and vector which is described Bloch sphere A1 multiplied by sigma Pauli matrices, and here we have second density matrix plus A2 scalar product with Pauli matrices. So this one, this density metric and this density metric describe pure state, and this one also pure state. But now we consider the mixing of these two pure state. So density matrix of mixed state, it is probability to find state psi1 plus probability to find in this mixing state psi2. So in density matrix which corresponds to mixed state, but this corresponds to pure state, and it can be written in such a way, and this one also operator which correspond to density matrix of pure state, some another pure state, and it can be written in such a way. Then as a result we can write this density matrix of mixed state in way the following: omega 1 density matrix of pure state rho 1 plus probability to find system in second state, probability omega 2 rho 2. So then using this representation for density matrices of pure states, we rewrite this result in such a way: omega 1, 1 over 2, 1 plus 1 scalar product here, plus omega 2, 1 over 2, scalar product. So we can combine this result to the following. Sum of these units gives omega 1 plus omega 2, which is equal to 1, of course, because it is probabilities, and we have only two possibilities, so sum of all probabilities is equal to 1. As a result, here we obtain this one and this one. Sum of this give us omega 1 plus omega 2, 1 over 2 plus 1 over 2, and here we have A1 plus A2 scalar product with Pauli matrices. So it can be written, it is 1. So we have 1 over 2 plus 1 over 2 A multiplied by sigma. And here I use the notation that sum of these two vectors is denoted as A. So what is interesting, you can find the density matrix of mixed state can be written in such a way as density matrix of pure state. Look here, it is density matrix. It is density matrix of mixed state, and this one is density matrix of pure state. But it is it looks in a very similar way. It is absolutely the same representation, but there is some difference. And now I would like to stress about this difference. Sorry, I must. В мене лекція, я перезвоню. 5 хвилин. Добре. What is difference between density matrix for pure state and for mixed state? Let us consider the length of this vector. length of this vector, which is 1 plus. So, but I forget. Maybe you find what I forget to write here. Omega 1, I forget to write here omega 1, and here omega 2. It is product. Vector A, it is omega 1 A1 plus omega 2 A2. Here we have product omega 1 and vector A1, omega 2, vector A2. So notation is the following. This vector combine two vectors A1 and A2, but with product omega 1 and omega 2. Here I forget, okay, here I forget to write omega 1, 1 plus omega 2, A2. So let us consider squared this vector, A squared, then is equal to omega 1 squared, and it will be A1 squared, which is equal to 1 plus omega 2 squared, and then plus 2 omega 1 omega 2 scalar product 1 plus omega multiplied omega A2, sorry. It is equal omega 1 squared plus omega 2 squared plus 2 omega 1 omega 2, and this scalar product, it is cosine. Phi, it is angle between these two vectors. So when we have two vectors, A1 and A2, and phi, here I denote the angle between two vectors. So we have here scalar product, which is cosine of these two vectors. So of course it is, when we here put 1 instead of this cosine, it will be less. It will be less than omega 1 squared plus omega 2 squared plus 2 omega 1 omega 2, and it is omega 1 plus omega 2 squared, which is equal to 1. So A squared, we find that A squared is less than 1. So we find that for density matrix, for density matrix of mixed state, Bloch vectors can be less than 1. So when we have equal to 1, so it means that we have pure state. But when this vector is less than 1, we have mixed state. So when wave vector length is equal to 1, we have pure state. And when this vector is less 1, it is mixed state, So we consider it mixed state for spin density matrix and have the representation for this density matrix. The main result is that for mixed state, a density matrix has the same form as for pure state, but only difference is that Bloch vectors, length of Bloch vectors is less than 1. All pure states corresponds to a sphere of radius 1. All mixed states is inside of this sphere. So it is just the main result of this paragraph. So maybe you have a question, comments. Time is over, so